So we have Advanced Classical Mechanics problem number 11 on the practice final exam. So here we have three equal masses, M lie on a frictionless line, and are connected by four springs of equal constant K, where we have wall, mass, 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 wall. And we let x of 1, x of 2, x of 3 denote small displacements from equilibrium. Part A, write the Lagrangian, the quadratic order. Part B, derive the matrix equation of motion. Part C, find the normal mode frequencies. Part D, find the corresponding normalized eigenvectors. Part E, interpret the physical motion of each mode. And Part F, discuss the answer changes if the middle mass is changed to 2m. So this is a coupled small oscillations problem. So we have three equal masses M, and they're connected by four identical springs K. So for part A, it's a wall M, 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 wall. So we let x of 1, x of 2, x of 3 be small displacements from the equilibrium. The kinetic energy is going to be T equals 1/2 M times the quantity here, x of 1 dot squared plus x of 2 dot squared plus x of 3 dot squared. And the potential energy here is V equals 1/2 K x of 1 squared plus 1/2 K times the quantity x of 2 minus x of 1 squared plus 1/2 K times the quantity x of 3 minus 2 x of 2 squared plus 1/2 K x of 3 squared. So our V here equals 1/2 K times the quantity 2x of 1 squared plus 2x of 2 squared plus 2x of 3 squared minus 2x of 1, x of 2, minus 2x of 2, x of 3. So from there we could say that the Lagrangian is going to be L equals 1/2 M times the quantity x of 1 dot squared plus x of 2 dot squared plus x of 3 dot squared minus 1/2 K row x of 1, x of 2, x of 3. And then we have this matrix here, first row 2, -1, 0. -1, 2, -1 for the second row, and 0, -1, 2 for the third row, and times this column, this x of 2, this x of 1, x of 2, x of 3. So that's the Lagrangian. So that's part A. Now moving along, building on this. For part B, we have the equations of motion here. So the equations of motion are m x double dot plus k ax equals 0, where A equals this matrix, first row 2, -1, 0, second row -1, 2, -1, and third row 0, -1, 2. Okay, so part C, all right, for normal mode frequencies we want to get here. So assume the normal modes, x of t equals a e to the I omega t. Then we have this quantity Ka minus m omega squared I times A. And A, being capital A, is the stiffness matrix, and lowercase a there being the mode shape vector or eigenvector, so the mode shape vector. So here the stiffness matrix A times the mode shape vector equals lambda times the mode shape vector. So lambda is going to equal m omega squared over k. The eigenvalues are lambda sub 1 equals 2 minus square root of 2, lambda sub 2 equals 2, and lambda sub 3 equals 2 plus square root of 2. So the normal mode frequencies are going to be lambda sub 1 equals square root of k over m times the quantity 2 minus square root of 2. Omega sub 2 equals the square root of 2k over m. Did I say omega or lambda? This is a omega sub 1. I'm sorry, I can't remember if I said lambda by accident. And then omega sub 2 is the following here, square root of 2k over m. And then omega sub 3 equals the square root of k over m times the quantity 2 plus the square root of 2. And part D, the normalized eigenvectors When we perform the computation, that's going to be for this a sub 1 equals 1/2 square root of 2 over 2, 1/2 for that column. For a sub 2 equals square root of 2 over 2, 0, negative square root of 2 over 2 for that column. And for a sub 3, that's going to be for this column 1/2, negative square root of 2 over 2, and 1/2. And for part A, we want to have the interpretation of this. So for part A, interpretation, mode 1, all masses move mostly together, with the middle mass moving more strongly. Mode 2, the outer masses move oppositely, while the middle mass remains fixed. Mode 3, the outer masses move together while the middle mass moves oppositely. Okay, and the part F, if we change the middle mass to 2m, so if the middle mass is changed to 2m, the stiffness matrix stays the same, but the mass matrix becomes m equals lowercase m times this matrix. First row is 1, 0, 0, 0, 2, 0, and 0, 0, 1 respectively for the rows. So the normal mode equation becomes k times that stiffness matrix times the mode shape vector equals omega squared times m times the mode shape vector. So lambda equals m omega squared over k, and the new eigenvalues are lambda equals 3 minus square root of 5 over 2, 2, and 3 plus the square root of 5 over 2. So building on that, for the remainder of part F, omega is equal to the square root of k over m times 3 minus square root of 5 over 2, square root of 2k over m, and the square root of k over m times 3 plus the square root of 5 over 2. So the anti-symmetric mode remains unchanged because the middle mass does not move in that mode. Okay, so that's all for practice problem number 11 out of 15 on the Advanced Classical Mechanics Practice Final Exam. Sorry about that. Thank you very much and have a great day.